And again, as was observed, so I mean, after scaling, multiply omega by positive constant, the Ricci doesn't change. So I can assume that lambda is either 0 or plus minus 1. And then you have the three cases, so I'm just going to repeat essentially what you said. Right? So this is the main case for us. So this is when the Ricci is 0, so this is kind of the Ricci flat metric. So Yau's, so of course this is only possible if this implies that C1 of x is 0, which I guess is a weaker condition than what I call Yau, so let's ignore that. But it's essentially the same. In any case, Yau's theorem implies that any Kähler class contains a unique Ricci flat representative. So let me briefly mention the other two cases. So do a negative curvature. So this is when lambda is, which one do I want to do? Say minus 1. So this is Ricci omega equal to minus omega. So this implies that this is only possible if C1x is negative. So this means that x is canonically polarized. And once it is, then, well, the theorem by Yau, or maybe Aubin-Yau, implies that omega exists, right? So, and is unique. Such a thing in that case. So canonically polarized was that Kx, the canonical bundle is ample. Is ample. So there are lots of sections. There are enough sections, so it's a multiple. So the canonical bundle gives you embedding into projective space. And then finally, this lambda is plus 1. So then you want Ricci omega equal to omega. And this is only this implies that x is Fano. So kx is minus kx is ample. But that's not enough, and as was discussed. So, well, it's a theorem. There's a lot to say about this, but let me at least say that Chen, Donaldson, Sun, many other people to mention, implies that in this case, if you're a Fano, then omega exists. Such a Kähler-Einstein metric exists if and only if x has some stability condition. I guess it's what they prove is exactly Kx is K polystable, which I'm not going to define. Okay. All right. Let me also say that instead of looking in the case, at least in the last two cases, or actually in all cases, I mean, so you can instead of, so in say in the case lambda equal to plus minus 1, you can instead of looking for Kähler metrics, I can look for metrics on the canonical bundle with some good property. So if I go metrics psi, I mean, it's not that it really helps, but it's a different way of formulating it. So I guess here plus minus. Well, I hope this right. Let's see. It's probably minus plus, but anyway, such that. In any case, but so you can look for this, right? So whenever when I have a metric on the canonical bundle, there are two ways of getting a volume form. So on the one hand, I can take the curvature. That's a 1-1 form. It's a Kähler form. I can take its nth power, and then so I can say that this. And then on the other hand, I can have this bijection between metrics on the canonical bundle and volume form. So I can write like this, and I think so. This is now, I guess, plus minus here, right, depending on where I am. Right? So this is kind of as volume forms on X. I mean, it's equivalent. Right? It's not that it's easier to solve that, but it's a different interpretation. And maybe as a similar remark, on the other hand, in the Calabi-Yau case, well, maybe I'll get to that later, actually. Let me know. I mean, in the Calabi-Yau case, I can also relate somehow the Ricci-Platt metric to the volume form, but in a kind of trivial way. Okay. All right. So now let me finally go to. I just wanted to set up this terminology to kind of to be able to talk a bit precisely about what I want to look at. Right. So here I have, so it's a map X from D star. So this is a map pi. So this is supposed to be smooth and projective. And I want this to kind of be meromorphic at the origin, right? So I mean, just explicitly, what does this mean? I'm not assuming anything about the fibers right now. So I mean, just you can think of this explicitly. So I mean, you basically have X sitting inside some Pn cross D star like this, and then you just have the projection, so D star. So this is just cut out by some suitable homogeneous polynomials, and then I'm assuming that the coefficients are then holomorphic on D star, but meromorphic at 0. Okay. So that's the kind of situation I want to look at. All right. So I want to, in principle, look at two possible cases, but I'm quickly just going to work through one of them. But in principle, there are two interesting ones. Go like that. So the relative, so there's a canonical bundle, but in this situation, I have the relative canonical bundle. So this is the one that has the good property that if I restrict it to xt, this is just the canonical bundle on xt. So it's kind of set up for that. Okay. And I'm going to focus on, so I kind of look at two cases. The first is when this kx over d star is trivial. So this is kind of the Calabi-Yau case. And in the second case, I want this to be, say, relatively ample. So it's example when I restrict it to xt. Well, in principle, it's the third case when you have fauna or whatever, but I think that's not really so reasonable. Let me focus and just say something about the first case. So the first case, so in the first case, so then you also fix L. So this is a line bundle on X, which I'm assuming is relatively ample. So this just means that L restricted to kind of xt is ample. I mean, I didn't say xt is the fiber over t here. Over something else. Okay? So this, if I have that, then by, not by Yau, means that there exists a unique, right? There's a unique omega 2 inside C1LT, which is Ricci-flat. So this gives rise to the whole yoga here. So I mean, you have that, and that gives rise to, in particular, you get a metric space, just xt to dt. You also get a volume form, which should be, say, omega t to the n or something on x. And for 2, it's kind of, let me just, since I'm kind of running out of time here, so it's basically similar. So then the question I would like to address, I mean, perhaps the more interesting question is what happens kind of in a metric limit. So here's kind of the question. So what can be said about these objects? Right. So what I mean, these objects, I mean, so you get, so if these are Calabi-Yau, you get some kind of metric space. And then it turns out that, well, there is a notion of Gromov-Hausdorff convergence. So you can put down a conjecture that these would converge in some Gromov-Hausdorff sense. And so that's very interesting, and not so much is known about it. And then I'll talk more about the case of what you can say about the convergence of these volume forms, which is easier to study, at least in this case. But you need to make sense of the statement, what the limit measure would be. All right, but we'll kind of take off from here next time, so I'll stop here.
Okay, well, thank you very much. Other questions, comments? Comments? Look, we have a coffee break, which consists of having some let's go around. They basically refer expanded, right? So yeah. So, but okay, this is not what I
So when you improve, so actually they can, if you improve, you can actually smaller equal to the constant glass, like 1 over maybe this guy, 1, okay, let's give this constant for us. Okay, so then you can add so this is one more thing about it. So this is how we have case. If you have one line for otherwise, so here, Mexico.